So in previous class I was teaching you about multimeter. So we have seen the application of multimeter. Multimeter can be used to measure AC current, DC current, AC voltage, DC voltage and resistances. So in previous class we had discussed about how a PMMC meter can be converted into voltmeter and to ammeter. Okay. So in this class we will study about ohm meter. Ohm meter is generally used for the measurement of resistance. Okay. So in ohm meter, here this is the circuit diagram of ohm meter. So in ohm meter, the battery is connected in series with one series resistor, and this is variable resistor. Okay. So what is the use of series resistor? Series resistor is used to limit the current, and this variable resistor is used to, this is also known as zero adjustment resistor. This is known as zero adjustment resistor. So we can adjust the deflection of this pointer to 0 by using this variable resistor. Okay, and this across these 2 points A and B we have to connect resistor, unknown resistor. Okay, so in this way we can measure the value of unknown resistor. We can use ammeter, we can use voltmeter, and we can use it as ohm meter. Multimeter can be used as ammeter, as voltmeter and as ohm meter. So ammeter can be used for the measurement of current, voltmeter can be used for the measurement of voltage, and ohm meter can be used for the measurement of unknown resistance. So how we can measure the value of unknown resistance by using ohm meter? Okay, so this is the battery, internal battery that is present in the multimeter, whose potential is E, and RS is the series resistance. It limits the current flow, and small r, this is variable resistor. This is used for adjusting the pointer to 0. That is why it is known as zero adjusting resistor. Okay. So suppose initially what we are doing, first A and B, these points are sorted. So sorted means it will show full deflection. This is PMMC meter or galvanometer. So if the two terminals A and B are sorted, then the pointer, it is showing I will be equal to IFSD. It is, the current is full scale deflection current. So now see this pointer. So suppose this is a 0 to 100 microampere range ammeter. Okay. So this is the pointer. So this will show at this position full scale deflection current. So for full scale deflection current, the resistance is 0. Okay. Then these 2 points are open. So for open case, the resistance will be infinite and the current flow, it is equal to 0. So at this case, the pointer, it will lie here, and corresponding to this current we are marking this as infinite ohm. Okay. So this is full scale deflection current. So corresponding to the full scale deflection current, we are marking here 0k ohm. Okay, so this is the scale of current. This is the current scale from 0 microampere to 100 microampere. So for the corresponding full scale deflection current, the resistance is 0, and for 0 deflection current means pointer where it is at 0, it is 0, then for this current it is equal to infinite. It is equal to infinite resistance. Okay, and for the known values of, then what we are doing, then suppose R is equal to say 5 kilo ohm, then for the known values of resistor we are measuring the current, how much current it is flowing. So for corresponding to that we are calibrating. Suppose this is calibrated 40 microampere. So for 40 microampere it is for 5 kilo ohm, the pointer is showing 40 microampere. So for corresponding to this 40 microampere we can write it as 5 kilo ohm. So in this way the instrument is calibrated. Okay, so we can see the resistance is dependent. Resistance is dependent upon the flow of the current. So if current is full scale deflection current, then resistance is 0. If current is 0, resistance is infinite. Okay, so these 2 points we are finding. Then for the known values of resistances, what are the values of current we have to find. Then based on that we can write down the value of resistances. Okay, so in this we can see that the current scale, it is linear, means this is 0, 20 micro, 40, 60, 80 and 100. But the resistance scale, this is resistance scale from 0k to infinite. It is not linear. You can see from 0 to 5, this division is bigger, this division is somewhat smaller, this is again smaller than this. So in this way it is decreasing. It is not linear. Whereas the scale of current scale, it is linear. So ohm meter works on this principle. Okay. So initially what we are doing, this rheostat or this variable resistance, it is used for zero adjusting, means it is adjusted so that it will show full scale deflection current by connecting this A and B terminals, sorting these two terminals. First of all, we are sorting this terminal, and this variable resistor, it is varied so that the deflection of the pointer, it will show maximum. So I is equal to IFSD, full scale deflection current. So for corresponding to full scale deflection current, R is equal to 0, and if we are opening, R is equal to infinite. Then what we are doing, for known values of resistor, what is the value of current, then we are marking. So in this way we are calibrating the meter. So this is the working principle of ohm meter. Okay, so you got it. So multimeter can be used. You have seen multimeter can be used for the measurement of current, for the measurement of voltage, and for the measurement of resistance. For the measurement of current, voltage and resistance. That is why it is known as multimeter. Means through this equipment we can measure many quantities, many electrical or electronics quantities. Okay. Then we will see about sensitivity. Multimeter sensitivity. What do we mean by multimeter sensitivity or sensitivity of an equipment? Okay. So sensitivity plays a very important role in any electronic equipment. Okay, so greater the sensitivity, you can write greater the sensitivity greater is the accuracy of measurement. Greater the sensitivity of the meter, greater will be the accuracy of the measurement. What does this mean? So first of all, what is sensitivity? Sensitivity, it is equal to 1 by I full scale deflection current. It is 1 by, it is the inverse of full scale deflection current, or it is equal to 1 by current sensitivity. And sensitivity, it is expressed in ohms per volt. It is expressed in ohms per volt. Okay. So suppose we have two multimeter A and B. Suppose this multimeter is A and this multimeter is B. Suppose its sensitivity is say 1000 kilo ohm per volt and its sensitivity is say 5000 kilo ohm per volt. Since the sensitivity of multimeter B is more than the sensitivity of multimeter A, that is why this multimeter will give more accurate measurement as compared to this multimeter A, since the sensitivity of multimeter B is higher as compared to that of multimeter A. Okay, so sensitivity plays a vital role Now, suppose you can see this circuit. Suppose this is 1.5 volt. Say this is 1000 ohm and this is 1000 ohm. Okay. And Rn and IFSD. Okay, D, and it is of now you can see, suppose this is an example, this is 1.5 volt and this resistor, this is RA and this is RB. RA is equal to 1000 ohm, RB is equal to 1000 ohm, is having the sensitivity of 1000 ohm per volt. Okay, we have to measure the voltage drop at RB. Okay, so without connecting this PMMC meter, okay, what will be the voltage drop across RB? You can see voltage drop across RB and RA, VRA, it is equal to VRB, which is equal to 0.75 volt. Why? Because both the resistors are equal, so voltage will be divided equally. So it is say 0.5 volt, 0.75 volt, and here it is again 0.75 volt. Okay, so 0.75 volt it is dropped across RB, 0.75 volt is dropped across RA, since these two resistors are of same value. Now if we want to measure the voltage across RB by using a multimeter, whose sensitivity is 1000 ohm per volt, and the knob is set at 0 to 1 volt range. Remember, the knob is set at 1 volt range. Okay, so you can see then sensitivity of the meter, sensitivity of the multimeter, it is equal to 1000 ohms per volt, and the multimeter is set at 1 volt range. So the total resistance of the meter, it is equal to 1000 ohm per volt into 1 volt, since multimeter is set at 1 volt range. So it is equal to 1000 ohm. So this is the resistance of the meter. The resistance of this meter is 1000 ohm at 1 volt range. Okay. So the figure will look like this. This is 1000 ohm, 1000 ohm. Again, this is 1000 ohm. Now the total resistance in the circuit RT, it is equal to how much? It is equal to 1000 ohm plus this 1000 ohm and this 1000 ohm, both are in parallel. So you can write like this. So it is equal to like this. It is equal to 1500 ohm. 1500 ohm is the total resistance of the circuit. So the current I, it is equal to how much? It is equal to it is equal to 1.5 volt divided by 1500. So how much it is equal to? It is equal to 1 milliampere. 1 milliampere. So the voltage drop at this point, say A and B. So VAB, it is equal to 1 milliampere into the total resistance. Total resistance at AB, it is equal to 1000 ohm in parallel with 1000 ohm. So it is 500 ohm. So it is equal to how much? It is equal to 0.5 volt. You can see this is 0.5 volt. Okay. Now see, actually the voltage drop at A and B, this is A and this is point B. Voltage drop at AB, it should be 0.75, but because of using this meter, with this meter, it is showing in the meter it is showing 0.5 volt. Okay. Another case, the same meter, but its sensitivity is more. Suppose 20,000 ohm per volt. Okay, then what it will show? Then in that case, and for the same range, 0 to 1 volt range, then in that case, first of all, we have to determine this resistance of the meter, resistance of the meter, it is equal to 20,000 ohms per volt into 1 volt. So it is equal to 20,000 ohm. Is it okay? Now the total resistance RT, so you can modify the circuit. Circuit will be looking like this. This is 20,000 ohm, and this is 1000 ohm, and this is 1000 ohm, and this is 1.5 volt. So we have to determine voltage at point AB. So for this, what will be the I? So for determining I, we have to determine first RT, total resistance. Total resistance is again 1000 ohm. It is in series with these two parallel resistors. So it is equal to 1000 into 20,000 divided by 21,000. Okay, 952.38, and this is 1000. So it is equal to 1952.38 ohm. Okay, this is the R total. Okay, then we have to calculate how much current. It is equal to, current will be equal to, I will be equal to 1.5 volt divided by 1952.38 ohm. Okay, so this is the total current which is flowing in the circuit. So we have to determine VAB. So VAB, it is equal to into resistance across AB. VAB, it is equal to the current, this current I into resistance across AB. So it is I is equal to 1.5 volt divided by 1952.38 ohm. This is the current, total current. And how we can determine RAB? RAB, it is equal to 1000 ohm in parallel with 20,000 ohm. This is 1000 ohm in parallel with 20,000 ohm. So it is equal to 1.5 volt divided by 1952.38 ohm multiplied with 952.38 ohm. So finally it is equal to 0.73 volt. So we can see that if we are using multimeter, here two multimeters have been used, multimeter A and multimeter B. Multimeter A has sensitivity of 1000 ohms per volt, and multimeter B, it has sensitivity of 20,000 ohms per volt, and both the multimeters are used for 0 to 1 volt range. The knob is at 0 to 1 volt range. Now we are measuring the voltage at A and B. Ideally it should measure 0.75 volt, but by using B, whose sensitivity is much higher than the multimeter A, it is showing 0.73 volt, and this meter it is showing 0.5 volt. See the difference? So by using a multimeter whose sensitivity is more, then its measurement will be much closer to the accurate value, so its accuracy will be much more as compared to the meter whose sensitivity is lower. Okay. So this is due to why this variation occurs. This variation occurs due to the loading effect of the multimeter. Okay. So we can minimize the loading effect. How we can minimize the loading effect in multimeter? We can minimize the loading effect. You can see. We can minimize the loading effect. This is due to the loading effect. We can minimize the loading effect in multimeter by choosing a multimeter whose sensitivity is more. So sensitivity, you can write, if sensitivity increases, then loading effect decreases. And second, if range, you can write voltage range is higher, then also loading effect decreases. You can see. Suppose A and B. You have seen its sensitivity is 1000 ohms per volt and its sensitivity is 20,000 ohms per volt. Okay. So in this case, you can see this meter was showing 0.5 volt and this meter was showing 0.73 volt. Actually, the accurate measurement was 0.75 volt. So if sensitivity increases, then accuracy of measurement also increases. Okay, and both the multimeter was at 0 to 1 volt range. Okay. Now, if we increase the voltage range, suppose the same meter means same sensitivity meter, 1000 ohms per volt. Now, if the range is higher, suppose if it is say 2 volt, then in this case the resistance RT it will be equal to 1000 ohms per volt into 2 volt. So it is equal to 2000 ohm. What does this mean? The resistance of the meter it increases if we are selecting higher voltage range, say 0 to 1 volt, 0 to 2 volt, 0 to 5 volt. So if we are choosing 5 volt, then the total resistance of the meter it will increase. Suppose one meter, this is meter A, 1000 ohms per volt, and it is selected at 1 volt range, and another meter B, it is having 1000 ohms per volt and it is selected at 2 volt range. Okay, then this circuit, the same circuit, so say this is 1000 ohm and this is 1000 ohm and this is at 1.5 volt. Now you have seen for this, so RT, total resistance of the meter, it is equal to 1000 ohm, and here the total resistance of the meter it is equal to 2000 ohm. So if in one case it is 1000 ohm and in other case it is 2000 ohm. So the total resistance it will change. Okay, so you can see if we are using 2000 ohm here, then this meter will show much more closer with 2.75 volt. So accuracy of this meter will be higher as compared to this meter. Okay, so we can see that the sensitivity of the meter plays a vital role in any meter for the measurement. So accuracy is directly proportional to the sensitivity of the meter. Now we will see about electronic voltmeter. Okay, so electronic voltmeter, this is the circuit diagram of transistor voltmeter circuit. In this transistor voltmeter circuit, one transistor, BJT transistor, is used. Okay, and this is PMMC meter, and this is series resistance. RS is the series resistance. This is PMMC meter. RM is the resistance of the PMMC meter. Okay. Now the voltage that we want to measure by using this transistor voltmeter circuit is applied across A and B, across base and this emitter across this. So this is the voltage that we want to measure by using transistor voltmeter circuit E. Okay. Now this is base current, this IC is collector current, and this IE is the emitter current. Now as we know that IC is equal to what? IC is equal to beta IB. Because of this voltage, current will flow, IB will flow, IB current flows. Okay, and this IC current, IC is equal to beta times this IB. So what is this beta? Beta is the amplification factor of this BJT transistor. Okay, because of E, IB flows, and because of beta and IB, IC is equal to beta times IB. IC is equal to beta times IB, where beta is the amplification factor of this transistor, and this is emitter follower BJT transistor. And you can see now IE is equal to IC. IC is equal to beta IB, and what is IE? IE is also this IM. What is IM? IM is the this full scale deflection current of this PMMC meter. Okay, so we can see that IM is proportional to beta IB. Okay, and this is also, this current is proportional to this voltage E. So we can say that the pointer movement in the PMMC meter, it is proportional to the applied voltage. In this transistor voltmeter circuit is used for the measurement of DC voltage. Okay, this E, this is the applied voltage, applied DC voltage. Okay, and this is VE and this is VBE, voltage drop across base and emitter terminal. So VE, this is VE, so VE is equal to this complete E minus VBE. So it is equal to, you can write VE is equal to E minus VBE, and IM is equal to, what is IM? IM is the current flowing in the PMMC meter. It is equal to VE, this voltage drop, divided by RS plus RM, where RS is the series resistance and RM is the meter resistance. RI is the input resistance of this transistor voltmeter. it is equal to this complete E divided by IB, okay. So this transistor voltmeter circuit is used for the measurement of DC voltage. E is the DC voltage, okay. So we can measure DC voltage by using transistor voltmeter circuit, okay. So here the current Im is proportional to E. In this way, transistor voltmeter circuit can be used for the measurement of any DC voltage. And one thing we have to remember is that ammeter is always connected in series with the resistor that we want to measure the current, and voltmeter is always connected in shunt with the resistance. Suppose we want to measure voltage across this resistance, then we have to connect in parallel, in shunt to this resistance for voltage measurement. And for the measurement of current, we have to connect in series. So ammeter is connected in series and voltmeter is connected in parallel with the resistance, okay. So what is the voltage drop across this resistance? It is measured by connecting a voltmeter in parallel with this resistor. And if we want to measure current, we have to connect ammeter in series with this resistance, okay. So it is clear about the working of transistor voltmeter circuit, okay. Then we will move about since this circuit is used for the measurement of DC voltage only. So how we can measure AC voltage? AC voltage can be measured by inserting a bridge rectifier circuit, by connecting a bridge rectifier circuit. So this type of circuit is also known as bridge rectifier voltmeter. So this combination D1, D2, D3 and D4, these are the four diodes which are used to make a bridge rectifier. So we can see, and this is PMMC meter, and we can see that the RMS value, it is always equal to 1.11 into average value. By using this, we can calibrate the meter in such a way that whatever the average value it is measuring, it will be calibrated in RMS value. So RMS value can be measured by using this type of bridge rectifier circuit, okay. See, suppose this is sine wave, and this is positive cycle and this is negative cycle, this is positive cycle and this is negative cycle. This is the input. So this is the input voltage that we are giving to point A and B, to point AB. So this is the input voltage. So during positive half cycle, suppose this is omega t, 0 to pi, 2 pi, 3 pi, like this. Say this is V peak and this is minus Vp. Vp is the maximum amplitude of this sine wave. So this is AC signal. So AC signal that we want to measure, we are connecting at point A and B, okay. So during positive half cycle, D1 and D4, diodes D1 and D4, it conducts, whereas diode D2 and D3 does not conduct, okay. So during positive half cycle, this is more positive, point A is more positive as compared to point B, and the direction of the current, it will be like this, from this, like this, like this, like this, and it will, this is the direction of current from A. This is a forward bias. This is also forward bias, like this, during positive half cycle. Similarly, during negative half cycle, we have to erase this. During negative half cycle, this D1 and D4, it will not conduct, whereas D3 and D2, these two are conducting. How it is conducting? It is conducting like this. The current flow will be like this, from this point this way, this way, this way, this way, this way, and this is not directly connected, it is like this way and this. This is the direction. Okay, so you can see this is not directly connected. This is not directly connected, like this. So we can see that during positive half cycle, diode D1 and diode D4 it conducts. During negative half cycle, diode D1 and D4 does not conduct, whereas D2 and D3 it conducts during negative half cycle. So in this way the circuit works. Okay, so and this PMMC, the deflection in the PMMC meter, it is directly proportional to the applied voltage, and it is calibrated in to measure the RMS value. So how it is calibrated? Whatever the average value it is getting, it is multiplied with 1.11. So RMS value it is displayed in RMS value. So we can measure AC voltage as well as DC voltage by using electronic meter. How we can measure AC voltage? By using bridge rectifier voltmeter, and we can measure DC voltage by electronic transistor voltmeter. Okay, so we have seen about multimeter, we have seen about voltmeter, okay, about electronic voltmeter, and we have seen about multimeter. Okay, so multimeter it measures current, voltage and resistance. So by using a PMMC meter, how it can measure current, how it can measure voltage, how it can be used for the measurement of resistances, we have seen. Okay, in multimeter. Similarly, we can measure DC voltage as well as AC voltage by using electronic voltmeter. So you can write rectifier, electronic voltmeter, and transistor, electronic voltmeter, that we have studied. We have studied about rectifier electronic voltmeter, we have studied about transistor electronic voltmeter. This is used for the measurement of AC voltage, this is used for the measurement of DC voltage. And multimeter can be used for the measurement of current I, for the measurement of voltage V, and for the measurement of resistance R. Okay, so we have seen about these two instruments, multimeter and electronic voltmeter. Okay.